click Apply. So this is the X and Y GPID as well as the acceleration. Right now, for whatever reason, it's not applying whatever these values are, it's applying the default values.
Okay.
So you'll just need to click Apply. And you just have to do that once anytime the software is open. So before tip approaching, at some point, you'll just have to go over to the TopoScan, open the scan parameters, and click Apply.
Mm-hmm.
After that, the entire time that the AFM software is open, it should be applied.
But do we have to do that only after the frequency tuning and everything?
No, you can do it before. So as soon as you open the software, if you want to, you can go over and click that. But it's just before you tip approach, you have to do it because it essentially what it will do. For example, if I change this value and click Apply, it might be hard to hear, but it didn't really do it. Typically what it will do is it will kind of click into place. And so if you're on the surface and those piezos move, then it will just ram your tip into the surface. So you want to do it before you tip approach, but you can do it at any point before.
Okay.
So then I'll go ahead and tip approach again. Okay, here we go, we're back on the surface. So I'll go ahead and check, say from 80 to 79, it moved. 79 to 78, it moved. From 78 to 77, it did not move, so I'll move 1 to 3% below that, so I'll just go to 76. Then you'll want to check your position, make sure that you're about halfway. In this case, I'm a little bit under. So I will just jog a couple of times, and we're right near the middle. It does not have to be perfectly, you just want it to be near that middle, both for the flexibility and for accuracy. So now, we'll go over the TopoScan window. So on the left, we have our scan parameters. You have the ability to change between a 2D and 3D scan. I recommend just keeping it on 3D. 2D will give you the X and Y data, but will not give you the Z data. So that kind of defeats the purpose of AFM. So I recommend just leaving that on 3D. Below that is rate and hertz. This is how rapidly each line will scan. So it's the frequency at which it will scan. The default value for this is 0.5. You can go as low as 0.15 and as high as like 40. I recommend never going over 1. The higher you ramp up that speed, the more chance that your ZGPIDs or your feedback system are not aligned properly for the speed that you're scanning, and you can break your tip. So I just recommend leaving it at 0.5 or slowing it down if you need a slower, nicer looking scan. Below that is lines. This will control the pixel density of your image. So it's essentially how many times that cantilever will go back and forth across the sample surface. The default for this is 256. That is 256 lines and 256 average data points per line. So it creates a 256 by 256 pixel image. It can go anywhere from 16 by 16, which over a 50 micron scan you're not really going to see much, all the way to a 1024 by 1024. I recommend sticking to 256 and 512. 1024, while the scans can look beautiful, it's going to take so much longer. Essentially, the difference between a 512 and a 256 is about 4 times longer. And the difference between a 512 and a 1024 is about 4 times longer. So even though a typical 256 image can take 8 to 10 minutes, once you start multiplying that out, a 1024 line scan at 0.5 hertz or even slower can take a really long time. And that's a lot of potential for somebody else to come and manipulate something and put just like a single line ugly mark in your scan. So especially while you're kind of getting used to using the AFM, running samples for the first time, don't go crazy and do a 512 or a 1024 if it's your first time running it. Take 128 or 256 scans to get an idea of what it looks like. Zoom in on your area of interest, and then take those higher resolution or those higher pixel density images. Below that, you have your X and Y gain sliders. I do not recommend manipulating these. For one, you should never manipulate these while you're on the surface. Similar to what I said before, it can cause those pieces to kind of crack into place because you're adjusting. Let's see. The X and Y gain adjusts the strain gauges that are mounted on the X and Y piezos. Those strain gauges force the X and Y piezos to move linearly. So typically with a piezo, say 1 volt makes the piezo move 1 micron. That does not necessarily mean that 2 volts will make it move 2 microns.
Yeah.
So it ends up kind of being a curve. And if you're trying to use it to analyze something like this, those curves can be very problematic. So those strain gauges are mounted on the X and Y piezos in order to force them to be linear, to where 1 volt is 1 micron, 2 volts is 2 microns. And it does this at the expense of some noise. So adjusting those values is essentially going to adjust the amount of voltage that's being supplied to the piezos and can cause them to kind of start to retract. So that's why you don't want to do it while you're on the surface, because it can cause those piezos to move and shift into place, and you'll just ram your tip against the sample surface. If you want to adjust these X and Y GPID values, you can. Again, it's not going to be something that we're going to cover directly. Typically what I do is, in the future, once you feel comfortable running the AFM, comfortable using the AFM, then we can hold some kind of meeting, or an email chain of some kind where I'll walk you through the process of adjusting these values. Typically, if you're scanning 5 microns by 5 microns or bigger, you don't need to adjust these values. As soon as you start going below that 5 microns by 5 micron size and smaller, then these values will need to be adjusted, because then that noise that those strain gauges create will become noticeable and it will look fuzzy. Additionally, XY acceleration should stay at 450. Shouldn't need to adjust that. Going over display, this is pretty straightforward. You have left image and right image. At any time, the AFM can capture 2 data channels. And so typically what this will be is your left image will pretty much always be Z drive or your topography, and then you'll adjust your right image. So you have several options. You have Z sense, which, as I said before, is a complementary topography technique. It should not replace your Z drive. It should be used in conjunction with your Z drive. We have Z error. This is where you're able to see your error signal. This is very important. You'll use this to adjust your ZGPID values here in order to ensure that you've minimized the noise in the system. So you'll use the Z error to adjust your ZGPIDs to make this noise, or this error signal, as small as possible. Then you have left minus right. In vibrating mode, this will do nothing. We'll just spit out a bunch of nonsense. In non-vibrating mode, this is where you're able to scan at 90 degrees up and down. in order to take a lateral force or a torsional measurement. And I'll show you that once we cover non-vibrating mode. For top minus bottom and top plus bottom, what this will do is this is just a live readout of your top minus bottom or your top plus bottom values as you scan. Several of these have been things that were requested by customers that we've provided, and they've just kind of stayed in the software. So it could be a case of where you'll never use it, or you could use it all the time. It just depends on kind of application and what use you find for them. Below that is Z phase. This is where you're able to look at your phase shift measurements. Z underscore ample. This will be a live readout of your vibrational amplitude. Realistically, it's going to look very similar to your error signal. And then aux ADC1 and aux ADC2. You will never use these channels. These are for auxiliary conductive devices, which in your case you don't have any conductive measuring tools, so you will not use those. Below that we have our background. So this just provides a basic leveling within the software. It does not change the actual values that are saved. All of the values that are saved from the AFM software are the no background values like this. And so you can see kind of what I was mentioning before in the presentation, that it's at a very slight tilt.
Mm-hmm.
And that's just because it's very hard to make things flat. Especially with, you have to keep in mind how many different things go into not only the AFM but also the samples. So the metal disc that the test sample is on, the dot of adhesive epoxy that holds that silicon chip on, as well as the actual flatness of the chip. So I think overall it's, in this case from right here, it's like 150 nanometer pitch from high point to high point. But this is going to be the data that is actually saved from the AFM. It's going to be the raw data, the unleveled data, and then from there you'll be able to open it in Gwydion and get a better idea of what exactly it looks like. So you have the option of line leveling and surface subtract. In this case it looks ugly because at the very beginning we weren't scanning anything.
Yeah.
But typically for this kind of sample, surface subtract will be the nicest. And then typically for any other types of samples where it's not repeating features like this, the line leveling will look better. But again, it will not change the actual data that's saved. Then you have my personal favorite. You have your optional colors. So you can go for magma, smooth, cool, warm. Again, it doesn't change the actual data that's saved, but it can kind of provide a little bit more of an impactful look. You also have light shading, which is another kind of visual technique. It's almost as if it's some kind of derivative technique that provides a much better kind of contrast of the actual sample surface. And then you have the option to add images. So for example, if you have an area that has high error, in this case you could add some of that error into your topography. Again, it's just visual. It doesn't change the actual values that are saved. Then we move on to the feedback. So we have a Z drive indicator, where 0 is showing when the Z piezo is fully retracted, 17 is showing whenever it is fully extended. And this blue indicator shows the actual position of its extent. I'm getting tongue-tied. Shows the actual position of its extension or retraction. The Z drive range, you can ignore this. It seems typically this updates every time you start the software, so in this case it was likely that whenever I started it before, the blue indicator was down there. And then the ZGPID will cover this once it actually starts scanning. but this is the gain, proportional, integral, and derivative values that you'll use to minimize your error. So, with that, I'm going to go ahead and start scanning. Which quickly, let me just make sure. Okay, yeah, that does look bad. And so it's hard to tell if that is just environmental or
Monitor at saka yung machine.